So yesterday I discussed about the rules that are employed while you try to produce block diagrams, and the importance of block diagram representation was also discussed. And when we came up with few rules, six in numbers, and here, these rules will be applied to systems which are represented by sequence of blocks in order to find a single block representation of that system, which indicates the transfer function of the system. So I told you what is the importance of block diagram reduction and why do we use it. We will now try to attempt a few examples and try to understand that how things are implemented in order to obtain a single block representation of system represented by sequence of blocks. So am I audible to all? Is my voice clear to all? I guess I'm audible to all. I don't see any response. All right. So starting with the first example. So let's say we're given a system represented by the following block diagram. This accompanies, let's say, six components which are represented by individual transfer functions G1, G2, G3, H1, H2, H3. So notice that specifically the term H in blocks are used for feedback loops. So if you are going to have a feedback within the system or within the block representation, that are specifically in most of the books represented by H. And the forward paths are represented by transfer function G. So here we have an arrangement of a system, block representation of the system. And we want to reduce this representation and want to have the final representation in a single block. So using the idea of the rules that we studied yesterday, we'll try to reduce it to final representation or in a form of single block. So now where to start from is not really important. It all depends upon you. So some of you might think to start from one point, and some others may be thinking to start from the other point. For instance, if you look at this problem, some of you might be thinking to start from this place. So you can see that this is represented by a feedback loop, and you can think to apply the second last rule, which was elimination of feedback loop. And some of you might look at this side and say that we would try to solve this loop first. So in fact, this is not a loop, this is a parallel path. And some might start from other place. So it's not really important where you start from. The thing which is important is you apply the correct rules. So on application of the correct rules, if you start from left or right, so whatever rule you pick, you will be finally reaching to a correct solution. So anyone starting from right side from this loop, other starting from left side, let's say from at this loop. So if you're going to apply, all of you are going to apply correct rules, then you'll be reaching the final solution, which will be same. So I start from this particular loop. So if you look at this loop, you see that this is a rule where elimination of feedback applies. So elimination of closed loop applies. So you have a forward path represented by G3, then the path which is represented by H3 takes its input from the output of G3. So input to H3 is taken from the output of G3 and then fed back to the comparator. So this is nothing but a feedback loop. So we will apply the rule which was given by elimination of summing point. So if you apply this rule, you see that you get a block representation which is G over 1 plus GH if this is minus. So here, since we have a minus symbol, and thus this will be represented by eliminating the closed loop, and then we'll be obtaining a block of this form. Since we had a minus sign here, so we had the feedback path with a minus sign. That is why we are going to take this as a plus sign. Now, if you look on the left side of this system, this arrangement, so we can shift this particular takeoff point towards right, because without shifting this takeoff point, we cannot simplify it any further. So if you're going to shift this takeoff point on the right side, then you are going to have a parallel path with this comparator like this. So shifting this takeoff point, and of course, if you're going to shift the takeoff point from this to this place, since this point was taking a signal x, if you assume this signal to be x, and you were getting a signal x at this side, at the input of the comparator. While if you're going to shift this particular point at this place, so it means that now on shifting the point, what you're going to get is a signal x times g2. So in order, you're supposed to now eliminate g2. In order to eliminate this g2, you will be adding a block with the gain or transfer function 1 by g2. So this is what we have done here. So we have added a block with the gain reciprocal of g2, since we were getting signal here xg2. And since you are going to feed this signal here xg2, which will be multiplied by 1 upon g2, and thus this g2 will be eliminated, and your final signal that you're going to give to the comparator will become x. Now again, so since you're picking signal from this side and another signal from this side, so you can reverse them. You can assume that if you're going to, because we say that the line, this particular line will be having, if this is a representation of an electrical system, then we say that this will be having same potential V. So no matter where you connect the takeoff point throughout this particular line represented by red, the potential will remain V. So this means that if we have a wire of, let's say, 5 volt, and we try to take a point from here, or we try to take a point from here, then they all will be having same potential of 5 volts. So irrespective of where you're going to connect these wires. So the same behavior applies here. So since this will be having same potential V and this will be having same potential, so we can interchange them, and we can assume that this line, we are going to connect this wire here, and then we connect this wire here. So it's not going to make any change or cause any difference to the system. So this can be done. So we assume now we shifted this particular point at this side. So what we get is a parallel path. Since we have studied that a parallel path is one where you are going to feed to the blocks same signal, and the output of each of the blocks will be fed to the comparator, either added or subtracted. That will be then taken into account in the final representation of the block in parallel form. And since you see that this particular path, so it doesn't have any block, so we assume this path to have a block with a gain of 1. So let me make this more clear. So we assume this path to have a gain 1. So in that case, now you have two blocks. One is 1 upon G2, the other is 1, which are connected in parallel fashion. So they are in parallel arrangement, and thus you can reduce them into this form. So now you get the sum of the two blocks, 1 and 1 upon G2. So this is the rule that was studied in, I think it was the second rule where we studied blocks in parallel. And I told you yesterday that there is no need to recite or remember any of the rules. You just simply understand them, and then you should be able to apply once you understand the concept of block diagram reduction. So here I didn't learn any rules here, and I can apply any rules. In fact, depending upon the knowledge or the concept of signal flows, you can apply any rule, but it should be correct. Now, if you look at these two blocks, or instead, let's see to this particular arrangement. So you have G2, this is the forward path. Then the output of G2 is fed to H2. So this is the feedback, which is again fed to the comparator with a minus sign. So you again have a feedback arrangement where you'll apply the rule 5, which is rule 6, which is the elimination of summing point, and thus this will reduce to this form. You eliminated the summing point to obtain the block reduced representation of that feedback loop. Now again you have these two gains connected in cascade or series. These two are connected in series, and then finally you have these two connected in feedback loop. So you are going to first multiply these two gains, then you're going to apply the rule elimination of summing point since H1 is the feedback part, and you're going to multiply these two gains. So now the reduced representation looks something like this. Now again, these two blocks come into cascade or series, then the first rule applies where you will be multiplying the gains of each of these blocks to get the final transfer function representation of the system. So this is the required transfer function of the system, which shown by example 1. So I think this is clear to all. Now if we talk about example 2. So now again we have blocks in a different arrangement, and you have to identify the rules that will be applied to each of them. So if you see this particular example, you'll see that there are two blocks straightforward connected in cascade G2 and G3. So these two blocks are connected in series. So they will simply be multiplied. And then you observe that there are certain blocks which have common input and their output are fed to the same comparator with certain sign. So H1, H2 and H3 are having common inputs and their outputs are fed to the comparator. So this means that they are connected in parallel arrangement. So the rule 2 applies to them. So you'll be having H1, and since you have a plus sign, so if you're going to represent these blocks by parallel combination, so in that case, in case if you're going to take the sign as minus, let's say we represented these blocks with a parallel combination, and whether they're going to be summed or subtracted depends upon the sign that we are taking at the comparator side. Since H1 is taking a minus sign, H2 is taking a positive sign, and H3 is taking a negative sign. So in that case you'll be having a sign change. For example, you could represent this by minus H1 plus H2 minus H3, but in this case you're going to then feed the signal to the comparator with a plus sign. Else the other way around is that you feed the signal to the comparator with a negative sign while taking H1 as positive, H2 as negative, and H3 as positive. So these two arrangement has no difference at all. They have the same meaning because you have taken a positive sign at this location. That is why you're taking negative here, positive here, and negative here. Had you taken a negative sign here, you would have been bound to take this as positive, this negative, and this positive. So they have the same meaning. If you're going to take this type of arrangement, the answer you will be obtaining finally will be same to the answer that we'll be obtaining using this arrangement. So there's no difference. So I'll be taking, let's say, negative sign, because I told you that most of the time we take the control system to have a negative feedback loop. So that is why we prefer taking it a negative sign. In that case, you will be having this arrangement with positive H1, negative H2, and positive H3. So this is what is written over here. So you combine these two blocks which were in cascade, then these three blocks they were given in parallel to obtain the final representation of this form. So let me clean the mess here. Now again, if you look at this particular arrangement, you see that you have a gain in forward path. So this is the forward path, and the output of this block is fed to this block in reverse direction or in feedback fashion, and this is fed to the comparator. So this again, the elimination of closed loop again applies, and thus you will be applying the same expression of G over 1 plus GH for elimination of summing point. So in this particular case, the forward path gain G is nothing but G3 multiplied by G2, while H is nothing but H1 minus H2 plus H3. So using this particular formula expression, and you will be substituting these values in place of G and these in place of H to obtain the transfer function or elimination of the loop, and that will finally be multiplied by the gain G1 in order to obtain the final transfer function that looks something like this. So from elimination of the loop you got this particular expression, and from the gain which is connected in series, you got this gain multiplied with the final cascaded gains. Likewise, here's an example 3. In fact, this example I took it from the presentation given by faculty Imtiaz Hussain. So it's a nice example, that is why I picked from it from internet. So suppose that you're given in a block arrangement in this fashion, and now you're required to solve it. So again, I tell you that most of you might be picking one rule, others might be picking second rule. So it's immaterial that what rule do you pick. The important thing is that the rule, whatever rule you pick, should be correctly applied. So suppose that we shift this particular comparator. So if you remember that there was a rule shifting of the comparator before the block. So if you're going to shift the comparator or the summing point, it was shifting of the summing point before the block from a location after the block. So if you're going to shift the summing point at this particular location, so what changes are going to happen? So again, you don't need to remember the rules. An easy way to understand is if you assume this as x, this becomes xg1. If you assume this as y, this becomes yh2, and the signal that you get at this particular point is xg1 minus yh2. So you picked a minus sign, you took a minus sign because you have a minus sign at this side of comparator, so which is the signal yh2 fed at this particular side, and xg1 has a positive sign in the comparator, that is why we are taking xg1 as positive. So the output of the comparator that you're going to get is xg1 minus yh2. Now in case if you're going to shift this summing point at this position, in that case what additional thing you're going to get is, so you can draw this in your rough copies, that if you're going to shift this comparator which was fed with the signal x having a plus sign and minus sign here, and now this signal is coming directly from h2 which was fed with signal y, the output of this comparator now goes through G1. So this particular output will be equal to yh2 with a minus sign, or I'll be writing this over here. So since x is fed to the comparator with a plus sign and yh2 is with a minus sign, so the signal that you will be getting at this point will be x minus yh2, and this will be multiplied by G1 in order to give you output at this location, which will be equal to G1 multiplied by x minus yh2. But what you actually required was the signal xg1 minus yh2. So the additional term that you are going to get is xg1 is the same term that you saw here, minus yh2 multiplied by g1. So this g1 is an additional term that you got compared to this expression. So now you're required to eliminate this G1. So how are you going to do this? By multiplying the gain H2 with the reciprocal of G1. So if you're going to multiply this H2 by the reciprocal of G1, then you will be getting signal here as YH2 divided by G1. And if this is fed to the comparator with input X, finally when this will be multiplied by G1, you will be getting the signal here as XG1 minus YH2. So I guess this is clear. If you, any one of you have problem in understanding, so you can stop me at that particular point and ask a question. So important is that you all understand what is being taught. So now if you look at this arrangement, then you'll find that G1 and G2. So this G1 and G2 are cascaded. So we'll be multiplying their gains again. And again, if you look, you have two possibilities. Either you shift this takeoff point towards left or towards right, or you shift this comparator on the left side, then you'll be having this as elimination of the closed loop. So now you can apply any rule, whatever you prefer, and people will have different choices. So you will be having different arrangements as you proceed, but you all will finally lead to same answer. So let us shift this. Okay, there's a possibility that you can interchange these summing points. So if I interchange these summing point, I get arrangement like this. Now the benefit of interchanging these two summing point is that these the forward path G1 G2 comes in closed loop with H1. So you again have a closed loop path, and then you can apply elimination of summing point to this in order to obtain G1 G2 divided by 1. Now you have a positive sign here. Note this. You have a positive sign here, which means that now in the denominator you will be getting a negative. So here we see we obtain a negative sign here because we were having a positive in the comparator. So you get G1 G2 divided by 1 minus G1 G2 H1. The same expression or formula that we studied for elimination of summing point. Now this particular gain and this gain comes in cascade or series. They will be multiplied like this. And then again this particular gain and this feedback path comes in closed loop and hence elimination of summing points applied, and you get the transfer function like this. So this is the, if you're going to take this as G and you're going to take this as H, then this will be G over 1 plus GH, where G will be substituted by this expression, H will be substituted by this expression to obtain the transfer function of that path given by this expression. Now again you have G as this term, and here H is 1. So you're going to take H is equal to 1. Since you have no block connected here, so you in such cases will be taking, you'll be assuming a block having value 1. H is equal to 1. So again, if you apply the same rule, then you get the rules that says elimination of summing point will be equal to 1 plus GH, and this plus is because you have a negative sign here. So you will be substituting in place of G this particular expression. You'll be feeding this in place of G, and in place of H you will be substituting 1 in order to obtain the final transfer function of final block diagram representation H. Now here is an example that we saw in Unit 1. We discussed about antenna azimuth position control system. So let us try to obtain the block representation. So in fact, this block diagram representation is given in Norman Nice, the book that I referred. So and of course you could see the components that correspond to different blocks. So if you talk about the input potentiometer, which is this, to which the theta reference angle was given. So this can be represented by 1 upon pi. Then you have a pre-amplifier which had a gain K. And again you have a power amplifier given by this expression. Then you have load and motor and gears which were represented by this particular expression. So different components are represented by different transfer functions which are connected in certain fashion in order to obtain the system or block diagram representation of antenna azimuth control. Then again, you have output potentiometer, which was working as a feedback and a sensing element, sensing the position of the antenna, comparing it with the reference that was fed to the input potentiometer. So this is in fact a block diagram representation of the system of antenna azimuth position control. And now we are required to find the final transfer function using block diagram reduction technique. So problem of such type is quite easier because things are straightforward. You have these three gains connected in cascade, so they will be multiplied, and then you have a feedback path. Then you'll be applying elimination on the closed loop. Then finally, after obtaining the gain for this particular loop, you will be multiplying it by the gain of the input potentiometer in order to obtain the final transfer function given as follows. So now this is your home assignment. If you like, you can take the snapshot, and I will be loading the lecture so you can look at this the video slides in the video as well. This is home assignment 2. The first assignment was given in Unit 1, and I suggest that you don't submit me the home assignments unless I announce the date for it. So it's better that you solve it, you keep the assignment along, and when I will announce the date, you submit me the assignment. So there are more questions that I will be assigning, and I suggest that you submit the assignment once I announce you the date. Here's the home assignment 3. So in this case, you are required to find the block diagram representation and reduction of the system. In fact, this is an example, I think a solved example from Norman is nice, so you can straightforward and obtain the solution from Norman is nice. But I suggest that you understand because since I will be taking your quizzes and exams, I'll be taking open book test. So it's suggested to all that you understand what is happening and how are things operating. Because if you look at this particular example, you are required to find the block diagram representation of the system and reduction. Since you're given a generator at this side, this is generator and this is motor. So this is nothing but a DC machine. And if you look, you have a field winding here, and the input is given at the field side of the generator, which means this is a field controlled DC machine. So you will be working similar to the transfer or the representation or the modeling of field controlled DC motor. You will be working the same, you will be applying the same principles to the field controlled DC generator here. Then again, the output from this generator, which is nothing but the armature voltage, is being fed to the motor. So the motor now becomes an armature controlled DC motor. So the transfer function or the modeling of armature controlled DC motor applies here. Then you will be having the output. So you provided an input in the form of EI to the field of generator, which provided EG as the voltage to the armature of the motor. Then you have from the armature or the motor, you have the angular displacement given to the gear trains. So modeling of gear trains was also done. Then you studied about the rotational motions, the mechanical rotational motions. So the final output is theta naught. So you are required to find a relation between EI and theta naught using block diagram reduction techniques. First, you will be representing each of them with a block diagram representation. So this becomes your home assignment, question 3. Here's a question that is not the home assignment, rather it carries bonus marks. So anyone who submit the question first correctly, the correct solution for this particular question, the first to submit this will get bonus mark. So this is all for today, and if you have any question, you can ask me.